Obviously, welcome to Chris. Chris Hodrien has spoken to us on a number of occasions. I met him through interest in stationary steam engines a great many years ago, and he's spoken to us on that subject, even on steam-powered submarines. But I think this is the first time he's been talking about where he actually spent his working life. So quite looking forward to some of that, much of which is going to turn up on the screen, so I shan't read the whole lot to you at the moment. Obviously, questions at the end, and when we get to that, Philip will just explain how people who are out online can put their questions in, which the system seems to be working reasonably well. So, I think with more ado, let's hear Chris on the joys of working in gas research.
Thank you. Good evening, everybody. Welcome to all the live attendees. I'll just talk about my own personal background for a second. I was made a chemical engineer at an early age. My two parents both worked in the same laboratory in Liverpool, so I kind of got the idea I would end up in an industrial chemical career when I was about 11 or 12. Went to Cambridge University, 4-year master's course in chemical engineering, quite rare at the time in Cambridge. That's interesting. I then worked the big chunk of my working life in British gas research for 27 years, led 27 different research projects in 27 years. People sometimes say, isn't it rather boring working for the same company for your whole career? Well, you know, the amount of variety, you'll just get some small idea of the variety tonight. We're covering about 4 of my 27 projects, I think, as examples. When I was kicked out, along with most of the rest of the research workforce in 2000 after privatisation, then had to find other things to do, so I've done a lot of freelance consultancy on energy and gas topics, mainly on gasification, which is my speciality, but also on carbon capture. And we're not talking about carbon capture much tonight. This is capture of carbon dioxide. There is no reason why the world needs to give up fossil fuels. It's perfectly technically possible to capture carbon dioxide for the exhaust, put it down a big hole, and keep on using fossil fuels more or less forever. As it happens, Britain has more holes under the North Sea in the form of empty oil and gas fields than almost any other country in Europe. There's even been talk of selling hole space to Europe for them to put some of their carbon dioxide in. And then alongside that, for a period, I was a visiting industrial tutor at Warwick University at master's level, teaching international students, and that was on bioenergy, so that involved a little bit of retraining. And the forward. Damn forward clicker's not working. Oh, right, we got there. Okay. Chemical engineering is riddled with jargon that's specialised to the sector, and British Gas is riddled with gas jargon as well. I've really tried very hard to eliminate as much as I can, but there are a few things left. I'm going to have to use a set of acronyms just for ease to speed the thing up. So here's a few of them. So NG is natural gas, MRS, Midlands Research Station, where I worked, TG, town gas. Now I'm very fortunate with my audience here. I'm sure all of you in the live audience are old enough to remember when we had to make gas before it came out of a hole in the North Sea. And most of you are old enough to remember the old-fashioned gasworks using coal that you could smell from about 5 miles away. We'll be talking about that technology quite a bit. One very important thing here is CV, gas calorific value. It's always done by volume in the gas industry because what gas pipes transport is volume rather than mass. So when we're talking about different gases, we have to look at their heating value by volume. Combined heat and power I'll mention briefly. US Department of Energy will feature at one stage, and there's a few units at the bottom here. And then the vexed question of gasometers. Everybody called them gasometers. That's not the technically correct term, they're gas holders. The gasometer was something that looked like a miniature version of a gas holder that was used for metering gas in the early days, and hence gasometer. But I'm going to use the terms interchangeably here because I know most people are familiar with gasometer. Okay. So what we're going to do first, we're going to have a very brief romp through the history of an entire industry from 1793 to about 2000. And we'll just whiz through what the industry was up to. I'll then rewind back and we'll talk about some of the technologies in more detail. So the original purpose of gas was for lighting long before gas cookers or gas fires had been invented. And the main initial purpose was street lighting, but also lighting for factories and eventually lighting for the home. So the basic discovery, small-scale R&D, call it what you will, was the famous engineer William Murdoch in his cottage at Redruth in 1793 in Cornwall. You can still see the cottage, we'll see it in a minute. The interesting thing is what's happened next. Most people that know anything about the history of gas have heard about Murdoch and his cottage. Murdoch and his cottage don't make an engineered process that you can sell to anybody. So there then has to be an industrialisation of the process on a rather larger scale before you can use it for lighting Mr. Lee's cotton factory in Manchester. Well, all that work was done at the Boulton and Watt Soho Foundry, Boulton and Watt's second premises, which is still standing. And we actually know from historical records which room all this development was done. It was in a basement cellar. The first, Boulton and Watt decided to exploit this technology first by lighting textile mills and factories. And they never quite got involved in the business of public supply. Public supply was promoted by other organisations, other individuals, and Boulton and Watt decided not to play, which I think was probably a huge error. They missed a lot of potential business. So the first public gas supply was Westminster in 1812, and it rapidly became the very legendary in the gas industry, the Gas Light and Coke Company. We'll understand why it was and Coke in a minute. Gas making is a piece of process engineering, is what we call it nowadays, and this bit long predates the origin of the chemical industry, which is where most people think process engineering came from. So you could say that Mr. Murdoch in 1793 is originating process engineering as well as gaslight. And just mentioning in passing, as with the railways and the canals, this all started out as private sector money-making business. It wasn't government-led. But what started to happen in the mid-1800s onwards is that a lot of town councils decided that they would buy up the local gas company, so they became municipal gas companies. That was quite common. Whiz through the history. I'm not going to describe all of these in details. Boulton and Watt have sold their first factory gas plant in 1803. From then, there's a few changes to the size and shape of the equipment, but basically the technology sort of stagnates for a long time. The 1850s, they're starting to add other processes that are needed for winter peak demand. It happens with lighting because there's longer lights of darkness in the winter. And of course, once people start buying gas cookers and gas heaters, the winter demand starts picking up quite a lot. Well, that's a problem because the basic gas retort Mr. Murdoch was playing with isn't really flexible. You can't really switch it on and off. It has to be kept hot all the time, a bit like a blast furnace. So you need something else that can be switched on and off. And that's the producer gas process using air, the water gas process using steam, and then its improved version, the oil carburetted water gas process. In terms of utilisation, as well as street lights, we have the limelight. Everybody knows the name. It's a real technology. You squirt a highly intense Bunsen burner flame at a piece of lime and it glows. So most places were using that. Gas cookers and gas fires and water heaters come along in about the 1850s. And it's a jolly good job they do, because in 1882, the first coal-fired electric power station opens in London at Holborn, Mr. Edison. And rapidly people realise electricity is really a far better method of providing light than gas is. Well, gas has to fight back. Now, all the early gas lamps are just open flames, and their luminosity is quite low. Fortunately, Mr. Welsbach invents the incandescent mantle, and many of you will be old enough to remember the incandescent mantle, I'm sure, old-fashioned gas light. It's basically a bag of what's originally fabric. You soak it in a thorium solution, you burn off the fabric, and you're left with an extremely fragile little bag of thorium oxide, which glows intensely white in a gas flame. It's still in use for a few very niche applications. Some people are still using it in camping tents. Some people are still using it in mobile caravans. This is a diagram of why the peak load was such a problem. This is over the months of the year, and you can see that there's well over twice as much gas being used in the winter as the summer. Now, this is an old diagram. This is from long, long ago. Because of the rise of central heating since the 1970s, this diagram has looked more like a factor of 5 in the winter. Major, major problem. How can you manage the gas system that flexibly? Well, can't we store it in those gasometers? Well, no. Gasometers are only capable of handling the swing between day and night, which is about a very similar graph to this. You know, not many people use gas in the middle of the night once all the gas lamps have been switched off. So the gasometers are doing the day to night swing. They simply don't have anything like the capacity, even though we had a fleet of about 800 of them, they didn't have the capacity to do this seasonal swing. So we'll talk about the technologies that are used for that when we get further in the talk. Right, I want to talk about CV, and I want to talk about a thing called enrichment. If you're going to change the type of gas you use, everybody's already got existing burners that fit the gas that came out of Mr. Murdoch's retort. If you now want to do something different, you've got to match the heating value, approximately, not exactly. It doesn't matter if the mixture of the molecules is the same or not. That doesn't matter. What matters is the heating value. So we're looking for a CV in old money of 500 British thermal units per cubic foot. Now, the problem with these seasonal processes, these ones you can switch on and off, the producer gas is only about a third of that. The water gas is only about 2/3 of that. And you have to find, what that means is you can only blend quite small volumes of it into the main gas. Otherwise, the average heating value will drop too much. Well, that was all solved with the carburetted water gas process, where some bright spark about 1900 realised if you squirted hot oil into the exhaust of one of these water gas generators, it would crack to smaller molecules like methane, and you could actually produce exactly the mixture you were looking for. Incidentally, the carburetted water gas process is one of the first ever processes to be fully automated, long before the chemical industry were doing it. It was, they had crude forms of automatic control on these plants. Okay, so let's have a gallop. Sorry, I may have missed one. Sorry, no, right. Okay, we're going to have a very, very quick gallop through the history of an entire industry, which is quite ambitious because it's a big industry. Following nationalisation in 1948, where about 950 individual gas companies became one organisation, it was split into 12 area boards. And I think most of you are old enough to remember the term gas board. Our local one was West Midlands Gas Board with its headquarters at Solihull. The gas boards have a real management power. They're the main thrust of the organisation because it's before it's been formed into an integrated company in 1973. However, there's an organisation I've mentioned at the bottom called the Gas Council. The Gas Council was formed in 1952 because it was realised we needed some sort of national level coordination of these people, and that's going to become more and more important as time goes on. And one obvious thing we want to do is we want to coordinate the research so as people aren't duplicating what they do. Virtually every gas board had its own research labs. West Midlands were at Nechells, for example, but there was a need to coordinate it. And also, the Gas Council, through the nationalised period, developed strategic plans for national system growth and investment strategy. Now, the landscape of how the gas industry was put together in 1948 was very, very different to what you're used to now post-privatisation. These were vertically integrated companies. They did everything. They made the gas, they transmitted it at high pressure, they distributed it to houses, they sold all the appliances. Most of you are old enough to remember the gas showroom. They did all the installation and servicing. They had their own large staff of gas fitters. They provided after-sales service, and they had very close technical relationships with the appliance manufacturers. They didn't actually manufacture the appliances, but they had a lot of influence in what the manufacturers did. So this is an era that some of us will fondly remember from before privatisation. Most towns had premises like this. So here's our local West Midlands board example. There's a photograph of its headquarters top left. The current headquarters, well, I say the current because it's gone now, but the one from the 60s to 80s was moved into Solihull in a brand new building in 1962, and that was on an old gasworks site. There's just an air photograph of the old gasworks that was there before. And this site was actually shared with the research centre where I worked. The company did a lot of business innovation as well as technology innovation. They really were right at the cutting edge of things. This was the largest open plan in office in Europe when it's opened, with over 1,000 people in it. It was so large that the postman had little electric trucks to drive between the desks. The business chief executives came from all over Europe to see this office, to learn how an open plan office worked. They deployed the UK's very first private microwave system, and that was handling billing from 3 million customers over a range of about a 50 miles radius. All the calls were being funneled into this one centre, and what they were doing there was what we now call the call centre. So if all of you hate call centres, you now know who to blame and where. The nationalised company inherited a stagnant and dying industry. The technology had not changed significantly since 1793. They were still cooking coal in pots, they were just rather bigger pots with a different shape. And the technology was stagnant. The technology required special grades of coking coal because you want to sell coke as a byproduct. And they were becoming in increasingly short supply, and when that happens, the price goes up. Unfortunately, the price they were getting for the byproducts of this gasification, which were mainly coke and various chemicals, they were all tending to decline at the time, so they were in a real crunch. The processes were extremely labour intensive, with high labour cost, and recruitment was getting more and more difficult, and in a few slides we'll see a picture of why it was getting difficult. The equipment had very high construction costs, inflexible production, and overall, the industry had an old-fashioned and dirty public image, just the same problem that steam engines had in British Rail in the run-up to 1968, versus electricity looked clean and modern. And electricity competition was increasing across the board, not just in the home with things like storage heaters, but in industry as well. So there's a graph of the stagnation. Now, if that had been allowed to continue, the gas industry might not have lasted long enough until North Sea gas was discovered in 1967. Little postscript at the bottom. The Northern Ireland gas industry, which didn't have access to natural gas initially, did die in 1991. The government sponsored all the gas users to go and buy electric fires instead. It's up and running again now using natural gas, but that's a different story. So, what research do we need to kickstart this old, dying industry in something that's got a chance of survival? Well, we're very used to using coal. So step one is let's use advanced coal gasification, and we'll be seeing some pictures of this in a bit. The advanced version of the gasification can use a much wider variety of coals, so you're not restricted to these expensive coking coals. It's higher efficiency. But more importantly, it's at higher pressure. And when it's at higher pressure, all the equipment squeezes down. If you double the gas pressure, you physically halve the size of the equipment. That makes it possible to build giant gasworks. So, for example, you could have one works supplying half of Birmingham. That was never possible under the old system, where Birmingham used to have about 10 gasworks with the old technology. And the one that was chosen was a thing called the German Lurgi process. Lurgi is part of the word metallurgischer, because it comes from the steel industry. It's a high-pressure process, originally invented in 1937, using steam and oxygen. And this is total gasification of coal. We're not just cooking it with a rather low yield of gas, we're converting the whole of the coal to gas. And this had already been used quite widely. The Germans had used it to run a vast synthetic oil fuel industry during World War II. They'd started doing it a bit before the war in 1933. And it's a very little known fact that World War II would have finished in early 1944 if the American Air Force and the RAF had succeeded between them in putting all these synthetic fuel plants out of action. Most of them, there were a fleet of about 12 of them, they were bombed at least 15 times each in attempts to put them out of action, and the Germans kept rebuilding them because without it they'd have had no oil for their tanks, no petrol for their planes. South Africa is less well known. There's a giant company called Sasol there. Coal was available for next to nothing in apartheid South Africa in the 1960s because it was dug by what amounted to slave labour. If you wonder how on earth the apartheid regime in South Africa was able to survive for so long against international condemnation by virtually every other major country on the planet, they had embargoes put against them so as they couldn't buy any crude oil. This technology kept them going. These plants are still running today. Very, very efficient, very, very famous in the chemical industry. So, this liquid gasifier has been demonstrated on German coals. That doesn't mean it'll work on British coals, because every coal's slightly different. So, the first job was to get hold of one of these gasifiers and to test it on British coals. So that was done initially at Nechel's, and then at Solihull when the research centre opened there in 1953. In 1961, 2 mega plants of this Lurgy technology were built, one at Coleshill, just down the road, and the other at Westfield in Fife, a bit north of the Forth Bridge. And this would have been the future of British gas, except that it was rapidly overtaken by 2 new technology revolutions. So I'm talking about a thing called naphtha reforming. Well, what's naphtha and what's reforming? Let's take a look. What's naphtha? Naphtha is the chemical industry's name for low-octane petrol. Just think petrol. At the time, in 1960, the oil refining company didn't have the technology to turn this low-octane petrol into petrol that was high enough to sell to you and me. So it became a surplus waste product available from most refineries at not much more than the price of coal. I know it sounds crazy that they couldn't upgrade the octane. You'll have heard of tetraethyl lead, but this was too low octane even for that. It's a lovely, clean, low-sulphur fuel. It's easy to store, it's easy to handle, you can pump it like water. It's tolerated by catalysts because it's relatively clean, and most importantly, it's got very low processing cost. So you've got vast quantities of this low-cost material of very good quality available, and this totally revolutionised both the gas industry and the chemical industry. There was a total revolution to use this stuff. The chemical industry using it still. So this is what the technology looked like. It was invented by the ICI Chemical Company in 1957. It's called a high-temperature steam reformer. So if you hear anybody talking about hydrogen today as a future possibility for the gas grid, and if you hear them talk about reformer, or SMR for short, that's what this is. What we've got a large series of long, thin catalyst tubes. They're about 30 feet long and about 4 inches diameter, containing the very clever ICI catalyst that's going to turn this naphtha and mixture of naphtha and steam into syngas, synthesis gas for short, which is a mixture of carbon monoxide and hydrogen. There's various different furnace designs. The process is highly endothermic. You have to put a lot of heat in to make it work, and that's why the whole thing's hanging in a furnace. So a third of the naphtha feedstock is being used in all these burners along the sides to fuel the furnace. So 70% is going down the tubes and 30% is being burnt as a fuel. So overall, you can make a process that is about 70% efficient. A few little details about the process here. Syngas is short for synthesis gas. Synthesis gas is amazing stuff. It's still the backbone of the global chemical industry today. If you have a mixture of carbon monoxide and hydrogen, you can choose any one of about 10 different kinds of catalysts, and you can make just about anything from it. You can make synthetic petrol, like the Germans were doing with coal gas in World War II. You can make hydrogen, you can make fertilizers, you can make all kinds of molecules, because they're both very reactive and there are catalysts available to convert them into things. So not only is it globally used today, I think something like 22 million tonnes a year of product last year, but it's a major option for making clean hydrogen for the future if we need a clean gas for the gas grid, for example. Now, we're back to this enrichment problem like we had earlier on in the 1850s. The town gas CV target we're aiming to match something that matches the CV of the existing conventional coal gas supply, because we don't want to do a national conversion back in 1960. So let's do a bit of clever process technology instead to tweak the thing around. Well, the basic ICI reformer only produces 350 BTUs, which is not good enough. So what they added was about 10% of butane, which has got much higher CV, and the mixture would get up to about 500. Well, the problem with that is that butane was very expensive. So what we needed was cheaper methods of doing the enrichment without using butane. And that's where Midlands Research Station comes in. These two processes here that we're going to talk quite a bit about, CRG, catalytic rich gas, and GRH, gas recycle hydrogenator, both of these processes came out of the same stable at the same time down the road at Solihull in 1960, just in time to avoid having to use vast amounts of butane. Now, to give you some idea of what we're talking about here, these plants cost about a quarter as much to build as a coal plant. They need less than 1/10 of the staff because they're almost fully automated. And the naphtha is very cheap. So long as the naphtha remains cheap, great. So now I want to talk about two huge revolutions in the production base of the industry. I think this is quite unique. I cannot think of another industry that has been through two total 100% revolutions in how it makes its stuff within a 20-year period. It really, the rate of technology change was just quite impressive. So we've already talked about the advanced coal gasifiers. Revolution 2 are the steam reformers. This starts with some rather crude cyclic low-pressure reformers in the 1950s, but the key thing is this continuous reformer, this ICI one here, and then the CRG and GRH added to it that allow you to produce a match for town gas. So the country, we built our last old-fashioned coal gas works in 1958. By 1967, when North Sea gas was discovered, we changed almost 100% to this new technology in 7 years flat, which is just quite extraordinary. I mean, the rate of change is ridiculous. And then comes Revolution 3. People discover gas, North Sea gas in the North Sea. Well, good heavens. At a quarter of the price. A lot of very high technology needed to bring it ashore. So it's during this time, I'm trying to mix technology and business changes here, that British Gas Corporation is formed, which is the organisation I work for. The whole lot is combined into one big national company. That goes on for 13 years, and then a certain female politician beginning with T decides we're going to privatise gas. And many of you will remember the Tell Sid campaign. Very, very famous in ever. So tell Sid to go and buy some gas shares. We're going to privatise the industry, and they wanted large numbers of the public to buy the shares. Ordinary people who'd never bought shares in anything before, you know, not stockbrokers. Oh, I've got quite a lot of them. To start with, British Gas was privatised as a single entity, but the government has this mania for competition. So they kept splitting the industry up. It's been split and split and split. And eventually Transco, which was the bit that was running the high pressure gas system, was merged with National Grid. So we now have the same company, who are based down at the Warwick Technology Park, just south of Warwick, are running both the power grid and the gas grid, which has caused problems of internal conflict of interest ever since. Just a couple of quick pictures of what CRG and GRH technology look like. CRG process is on the left. Again, it uses, well, both of them use naphtha. So CRG is a lower temperature version of the ICI reformer we were just looking at, but it has a much, much more active catalyst, like about 10 times as active, which allows it to operate at much lower temperatures. Why is that important? When you operate at lower temperatures, the equilibrium of what you make swings, and you make mainly methane, which is much higher CV than the 350 we were getting out of the ICI reformer. So what this allows you to do is to mix together reformer gas and this gas to make this town gas mix of 500 that we're looking for. It's a very simple process. It's a single fixed catalyst bed. And the other thing that happens when you operate at low temperature is the heat balance changes. So instead of being endothermic, this reaction now becomes exothermic because methane's being made, and the reaction will just run itself. It doesn't need to be set in a furnace. So you've saved 30% of fuel. The GRH process on the right is an amazing technology. It doesn't use a catalyst because it's far too high temperature to use a catalyst. It's an empty reactor. You're simply reacting naphtha vapor and hydrogen, which you make from that ICI reformer, But what's clever about it is you can see there's an internal recirculation here. There's an internal recirculation tube. And the reason you need that is that this reaction is viciously exothermic, and if you don't keep the gases well mixed together, they'll form hot spots and melt their way through the side of the reactor. So that's a really key part of making that technology work. So what's the result of these technology revolutions? Well, I showed you the stagnation graph a few slides ago. Well, this is the gas graph here. You can see the coal share in the UK's energy use is rapidly reducing. Electricity is increasing, but not dramatically. But look what gas is doing. It's going up fivefold. Oh, oil, by the way, is just a bit player in heating. Never been a big player. So gas becomes the story. But how many of the public know it? Yeah, you all take it for granted you've got gas central heating. I presume you all have. So here's 2.5 technical revolutions, as I'm calling it, within 20 years, sandwiched onto one slide. Top left, we've got the top of the gasifier vessels at Coleshill, just down the road, long since demolished. They became obsolete overnight when steam reformers started coming in using naphtha, because this was much cheaper technology, about a quarter of the price to build and virtually fully automated, very few staff needed to run it. And then all that gets replaced by North Sea gas. Well, you can't move North Sea gas around without a national gas grid. We never had a national gas grid before this. Gas was made in the towns where it was being used. Coleshill supplied Birmingham, it didn't supply London. So this gas grid has to be created from scratch using extremely high pressure pipes, because you need to compress these vast volumes of gas down into a sensible size of pipe. Now, one pipe of about 1.2 metres diameter can shift about as much energy as 20 coal-fired power stations. We only needed about 4 major pipes coming down through Scotland to supply the whole country. Total dramatic revolution. Now, the natural gas conversion. The problem with natural gas is it's got twice the heating value of the old town gas, so you now need different burners. It's twice the heating value and about 10 times, about a tenth of the flame speed that hydrogen had in the old town gas. The entire country was converted in 10 years. That is quite extraordinary. It required enormous strategic planning at national level by the Gas Council. A complete bespoke management team was put aside. Here's some statistics here, just to give you an idea. Feel the width. You know what happened in your own road? Well, this is what the big picture looks like. 13 million premises containing 35 million appliances. Commercial and industrial, another 500,000 premises with another 2.5 million burners. Every single burner's got to be replaced. It's got to be replaced right first time. It's got to be replaced safely without blowing people up. So you need a labour force of 11,000 staff, all of whom have to be specially trained on natural gas burners in 13 colleges. It's like running World War II. So it's widely regarded as the UK's largest ever peacetime operation for any purpose. And British Gas was enormously proud of the success of this operation. Along the way, we created the entire new national gas grid you just saw, which didn't exist before. Total costs in 1977 values, it's a little under 600 million for the whole exercise, of which creating the national gas grid, cost about 110 million. You've got to multiply those numbers by about 6 to today's prices. So we're looking at 3.5 billions worth of stuff. The remarkable thing is, the company got no help from the government for this. It was all funded by borrowing, and natural gas was so cheap compared with manufactured gas, it had all been repaid by the end of the conversion in 1978. Quite extraordinary. At this time, companies like British Rail are requiring massive bodges of government subsidies to stop them going bankrupt. It's an incredible exercise. Now, there's a technical thing which a lot of people don't know about, the calorific value dividend. Because the natural gas has got twice the calorific value per cubic foot of the old gas, all of a sudden, the entire network, every pipe under every road to every house, can carry twice as much energy. We've been living off the fat of the land of that change ever since. Big problem if we change the gas grid to hydrogen now, because hydrogen's only got about a third of the heating value. So the energy transmission of the gas grid would drop by 2/3. Bit of a problem. I presume many of you can remember the old town gas being flared off at the end of your road. The conversion was done in a single afternoon in each road by road. And the whole thing ran pretty much like clockwork. We didn't even have to change the pipes under the roads. They all stayed the same. Some of them dated from about 1812. Okay, so just a quick flash of the national grid being constructed. Just to explain, British Gas did not provide the technology for these gas pipes. It was all bought in, most of it American technology. But we were responsible for funding it, planning it, and all the rest. So how does the whole system work? We've got something like 280 oil and gas fields have been used at one time or another in the North Sea over the last 50 years. An extraordinary number. That's why I said there were so many holes available to put carbon dioxide down. All of that feeds into just 5 shore terminals, 4 on the east coast, 1 on the west. And now in this new era where we're importing liquid gas by tankers, we have 3 liquid gas importing terminals as well. And now we have 4 gas interconnectors, as they're called, much like electricity, to swap energy to and from the continent. So 2 of them go to Belgium and Germany, and 2 go westwards to Ireland. We run most of Ireland with our gas. The national transmission system, the high pressure stuff, this stuff, is 5,000 miles. It was built in less than 10 years. The distribution networks, which is what the gas industry had built over the previous 100 years odd, is 176,000 miles. I think that's more than once around the equator, if I remember. So this is where the gas comes from. This is the simple version. Now on this chart, the oil fields are green and the gas fields are red. So you'll see there's this big group of gas fields down the south, offshore Norfolk, that sort of area. There's a sprinkling in the middle, but not many. They're mainly oil. And then there's another big group of gas fields around here. That's the simple version. Just a quick snapshot. This is the real version. This is the real version showing all the interconnecting pipes that connect all these oil and gas fields to the shore. This is one's annoying. I'm afraid it's the other way around. The gas fields are now green. I've highlighted 2 gas fields at the top. These ones with the circles. And I've also highlighted this sector boundary. This dotted line up the North Sea defines what's owned by Britain and what's owned by Norway, or down here by Denmark and Holland and so on. By a stroke of geological accident, most of the oil and gas are within quite a short distance of the boundary. And it's quite arbitrary which have ended up on which side. This is just a piece of accidental geology, nothing to do with modern politics. But what I've highlighted is 2 gas fields at the top. The 2 largest gas fields in the North Sea are not in the British sector at all. They're Frigg and Troll, and they're in the Norwegian sector. Well, don't the Norwegians want their own gas? Well, not really. They've got a population of only 5 million, and because they have such cheap hydroelectricity, electricity is cheaper for them to use, so why bother? So it was much more convenient for them, mutually convenient for them to sell it to us. So the UK has been self-sufficient in North Sea gas right until 2003. We have never been self-sufficient in British gas. That's a little secret you don't hear much. A few quick statistics. I couldn't get all these on the same time period, but you get the idea because they all overlap with each other. Investment in North Sea oil and gas fields went up 16-fold, resulting in a production increase of 3-fold in 7 years and 9-fold over 20 years. At the same time, gas consumption, because you all rushed out and bought gas central heating, went up by a factor of 3. And the gas share of UK energy passed coal in 1993. A lot more recent than you might think, perhaps. But coal had been the vast majority of UK energy before. North Sea gas production peaked in 2000. That number. Sorry. And by 2022, it was down to that number. That shouldn't surprise and shock anybody. It's like digging rocks out of a quarry. If you keep digging it away, there's going to be less of it left. So we're now down to about a third. And as a result, gas imports are now over 50% and rapidly rising. But don't panic. This includes what's coming from our good friends, the Norwegians, that are still selling gas to us at very advantageous rates. All this panic you hear in the press about buying gas from Putin, forget it. The Hungarians and the Germans were in real trouble with Mr. Putin's gas. We only import about 5% of Mr. Putin's gas, so don't worry. It's not actually a problem. So, the achievements of British Gas Corporation as a nationalised organisation from its formation in 1973 until privatisation in 1986. We've got completion of the National Grid project, UK's largest ever peacetime project for the conversion, resulting in a ballistic expansion of the industry. Most of the public are really not aware of these statistics at all. They're carving increased market share, particularly against coal, this graph again. And the gas share of central heating in people's homes is now about over 90%. Which is why the government trying to decide everybody to have a heat pump instead is probably bonkers. Huge technology revolutions have driven this. This would not have happened without technology revolutions. Gas might have quietly died. It happened because this nationalised industry was engineer-led. It was led by engineers of real vision with the tools to make it happen. British Gas, I like to think, is the world's best gas company. It had a tremendous reputation for competence, for safety, for modernisation, cleanliness, all these things. And yet still we have this dreadful negative press that kept on whinging on about the old individual gas fitter that hadn't brought the right tools to mend your boiler. You know, we have probably the most negative press in the world. Huge global reputation within the gas industry for technology. We have sold technology to virtually every country on earth. Technology and advice, how to run a gas grid. Interesting thing with these nationalised industries, this applies also to British Rail and National Coal Board as well. There was a very interesting arrangement. I said British Gas was engineer-led. The government of the day, back in nationalised days, very sensibly decided it would be good to let the professionals plan the strategic future, which the government then rubber-stamped. And that system worked extremely well until a certain female politician came on who thought she knew better. That's why all this has worked like clockwork for so long. Gas industry, highly profitable for government, unlike certain other organisations we can mention. And it was the joint best nationalised industry, jointly with the CGB, who were a world-class organisation as well. Just a quick jump right forward to privatisation before we get back into the technology. What's happened since? Well, the natural gas was always produced by the global oil companies, and British Gas simply bought it at the beach. But we used to have monopoly purchasing rights, which is a massive advantage for British consumers. They were able to negotiate a really sharp price at the beach. It's now split among maybe 35 gas suppliers. The gas piping network, that's this national grid and everything right to your house, is run on a common carrier basis, a bit like Network Rail or whatever they call it these days. One company owns the tracks and everybody else is free to play putting packets of gas along it. And the profits of this common carrier are very strictly regulated by government. We've got 7 gas storage companies providing storage to handle that winter to summer swing we were talking about on 12 sites. Thanks to idiotic government decisions, the 12 weeks supply that we used to consider adequate is now down to 1 week peak winter day supply. Bit tight, some would say, some engineers would say. Our continental cousins think it's necessary to have 3 months' worth. The way they run, they think that's a sensible amount of gas storage to balance your system out. We have 3 liquid gas tanker import terminals. They've been going for about 20 years now. We've got about 35 competing gas suppliers all trying to compete with each other on price, running gas through this common carrier network. And they tend to split into residential ones, which you hear about all the time in the press, and ones who specialise in industrial gas supply, which you tend not to hear about. So what have we got now? We've got horrendous commercial complexity, the armies of contract lawyers. We've got a distinct lack of central planning coordination and quite a lot of wasteful competition taking place. And you know what they say about a house divided. Right, let's jump into some technology, shall we? Let's go back to Mr. Murdoch in 1793. What's this process he's using? Its technical term is carbonisation. You simply cook coal in a retort at a little over 1,000 centigrade for about 8 hours. And this basic process was in continuous use all over the world from 1803 until about 1958. That was when we built our last plant of this type. You then take this hot gas out, you cool it and condense water out of it, because you make quite a bit of water in the process, and you extract and sell various useful things like ammonia and coal tar and phenol. Well, I can remember in my school lessons, and one or two of you may, seeing the diagram of the 100 different compounds you can make out of coal tar, including, would you believe, aspirin. There was a massive coal tar refining industry. It was quite a big part of the... oh, and some of you will be old enough to remember National Benzol Petrol. That was coming out of these gasworks as well. It's the light fraction of tar. You then have to purify the gas because it's full of all kinds of nasty sulfur compounds, which is why you could smell these gasworks 5 miles away. Hydrogen sulfide, ammonia, cyanides, and this is done by washing with water. Most of these things dissolve in water. And then by lime initially, solid lime, you pass the gas through a bed of lime, and later on through dry iron oxide, which was cheaper and better. The retorts are run under slight suction. That's quite deliberate, because then if there's a leak, air will leak in rather than gas leaking out at 1100 centigrade. So you then need a gas compression unit, a thing called a gas exhauster, driven by a steam engine, which is driven by a boiler, which is driven by the waste heat off the retorts, to push it into the gas holder. Now, the pressure in the gas holder is extremely low. I know they're big, impressive-looking things, and you think, good heavens, we're lifting 100 tons in there. The pressure per square inch is tiny. It's significantly less than the pressure you blow a balloon up with yourself, which makes it a very safe system. And these gas holders, or gasometers if you prefer, are doing the day-to-night flow balancing and covering you over the weekend. Then through gas mains to gas lamps, remember, in the streets, and subsequently to houses and factories. A few little pictures. There's Mr. Murdoch on the left. I'm sure some of you are familiar with this portrait. And most of you, I'm sure, are familiar with the statue in Broad Street. Mr. Murdoch is the third man. He's the man at the back. This is the thing with the nickname of the carpet salesman for very obvious reasons. So we've got Boulton on one side, Watt on the other, and Mr. Murdoch, the brilliant engineer, at the back. And here's the cottage. This is where it all happened. It's now a museum run by a community group. Unfortunately, it's only open on Friday mornings, but if you're ever down that way, Redruth way, do go and have a look. I'm afraid there's a very good exhibition on Murdoch inside. Lovely little diorama here. This is a diorama the Science Museum had commissioned in about 1950. Here's Mr. Murdoch lighting up the world's first gas light. And here's a passing Cornish miner on his way home from work, wondering on what on earth is going on and where are the candles. I mentioned there were other promoters promoting gas light in London, so this was an early demonstration of gas lamps in Pall Mall, first ever demonstration of street lighting in the world. We have outstanding early gas infrastructure surviving in the West Midlands area. This fella, the Boulton Foundry, Soho, which Smethwick, which Jim knows extremely well, is where it all happened. This was where Boulton made their engines after 1795. The actual basement cellar, which was Mr. Murdoch's gas research lab, has been identified by modern archaeologists. We know exactly where it is. Problem with this, you can't get in it. It's a huge embarrassment to English heritage. It's one of the world's most important industrial buildings. The estimated cost of putting the roof right is at least 8 million. And it is at the back of the old Avery weighing works, now owned by an American company. So it's at the back of the works, which makes public access very difficult. But it is there, and it is important. But down here in Gas Street, you all know Gas Street. You all know Gas Street means it must have had a gasworks once. Well, even Chris Hodrien didn't know that it still had its gasworks in 1990. It's an amazing discovery. Turns out this bit, the square bit, is the oldest surviving gas resource house in the world, as far as we know. Then down at Warwick, we've got a very strange thing. They used to think it was a jolly good idea putting gas holders indoors. So as if they weren't banged, the brick walls would stop the debris getting out. They rapidly discovered all it did was make lots and lots of brick shrapnel. So these were probably almost the first and the last gas holder houses built, 1822. I mean, they were completely abandoned within a couple of years of this fella. But it's still there, beautiful building. The gasworks behind it has gone, but the building's still there. So here's a lovely Science Museum model, not of Mr. Murdoch's cottage, but of the scale-up I was mentioning that took place at Boulton and Watt. This is what turns the technology into a saleable proposition, initially for supplying factories, mainly textile mills, with gas light to replace thousands and thousands of candles. You might think gas is quite hazardous, but trust me, it's a lot safer than a candle. You can't knock a gas lamp over on your desk. So the technology has now evolved into large baskets of coal being dropped into pot-shaped retorts for about 8 hours at a time. Now, this is not a very good system because it's incredibly hazardous for the operator getting a basket of white hot coke out again at over 1,000 centigrade with gas flying all over the place. So it rapidly changes into the horizontal retort technology. So these retorts are about 10 to 12 feet long, only about a foot wide. You can see the ends of the three of them here. So you're looking into that building in Gas Street. This is an example of what would be in that building. And it would be open-sided exactly like this one is for gas safety. This is not just a cutaway drawing. This is what they actually look like. So the front wall was missing quite deliberately because you don't want inflammable gas built up in a building. So we have the retorts here, we have the purifier here, and there's metering and so on going on there, and then off into the pipe under the road. So this fella is still there standing in Gas Street, but minus all its insides. So we then develop what's called the bank of horizontal retorts, and typically they're in banks like this. You get between about 5 and 8 in a bank, and then if you want more, you build more banks. Now, working in this is about the nearest thing there is to working next to an active volcano. The stuff is coming out over 1,000 degrees centigrade, emitting large amounts of gas as it does. So it's all rather exciting. And this was why they were having such difficulty recruiting new men to do this in the 1950s, because social attitudes had changed a little bit. 1860s, they've grown a lot bigger. So the left-hand one is Nechel's, and the right-hand one is Saltley. We've got railway tracks feeding them, large coal handling systems. A couple more pictures. Now, we've started to mechanise. This machine here that's running on railway tracks is a coal projector, as it's called, that can actually throw coal into the retort to save the men having to throw it in with their 10-foot-long shovels. Next step is to have a double-ended retort that's open at the other end, and then the machine can also have a ram that will push the residual coke out. This is the last gasp of this technology. Mr. Murdoch would recognise this, the last gasp. Millport Gasworks, taken by Chris Allen, on an island in the Clyde. Because it was isolated, it hadn't been convenient to change it. And that's not quite the last shovel full of coal going in, but it only lasted about a year after this picture was taken. They were still recruiting stokers to do this job in 1978. Now, I wonder where they got them from. Here's some more pictures. So on the left, we've got the classic horizontal retort house with the big charging machine again. This one's at Fulham. And on the right, we've got the advanced version I talked about. We're scaling this technology up. It's the same technology. Well, what's a good idea to put it vertical so as the coal will shuffle down by gravity by itself? All you need is some sort of grinding apparatus at the bottom to grind the coke away and let it drop, and the whole charge will shuffle itself down the retort. So you can take what was an intermittent process for about 8 hours into something that's now continuous. You can feed coal in the top, and white hot coke will come out the bottom, and the whole thing runs much, much more efficiently. But the basic process is still the same. All you've done is change the way the pot works. Now, that's all research. They didn't call it R&D in those days, but that's what it was. Where can we see this technology today? Well, if you want to go and see the little village gasworks, there's only 3 places in the UK you can do that. Fakenham in Norfolk, Big R in the Scottish borders, and Carrickfergus in Northern Ireland. They've each got a complete village gasworks. I've still got a copy of the memo from British Gas to the government asking Fakenham not to be preserved because it was old-fashioned dirty technology that wasn't good for our image. But thank God the Science Museum overrode them. Now, you should be able to see gas equipment on display in our science museums, and that's a big problem. The Science Museum never had very much equipment, but they did have an excellent gas gallery, of which this is the booklet, that properly told the story from Mr. Murdoch to about 1960. In about 1980, that was all swept away because they got very tempted by a big grant from the big North Sea oil and gas companies to have a new display all about how gas is produced now in the North Sea. So most of that is in store now, which is a shame. Now, there was a complete retort bank, replica one, at the Manchester Science and Industry Museum, and I'm sad to say that was actually closed in 2015 and all the stuff is in store. I regard both of these as institutional vandalism, by the way. The Science Museum doesn't always do the right things. Large urban works, like that big vertical retort you just saw, zero. There is no preserved example in the UK at all. If you want to see one, you'll have to go to one of these three places. I've been to the New Zealand one and very good it is too. I think it's very sad we didn't preserve at least one as a representation of this huge national technology. Let's look at the utilisation side. 1882, here's our problem. Mr. Edison and his electric light, do not use match. This is genuine, by the way, it's not a modern joke. These were distributed by the tens of thousands. There's the old-fashioned type of gas light with open flames. And if they'd stayed with that, electricity would have kicked them out the door within about 5 years properly. Here's the Wellsback gas mantle, this glowing piece of thorium oxide that saved gas lighting into a slow, steady decline through the 1950s, but at least saved it. And this is gas fighting back. This is a poster from about the 1920s, I think, or maybe even more recent. Yeah, they're saying gas light's better for you. Interesting, eh? And then you've got modern appliances being developed, thank God, otherwise the industry would have more or less collapsed. You've got gas heaters, gas cookers, and all the promotion to go with it. So these are fairly modern promotional posters from the 1930s. I think that's a 1920 one on the left. This carbonisation process I keep talking about, cooking coal in a pot. Well, it goes by different names in different industries. If it's in the gas industry, you call it a gasworks, because what you want is this purified gas, which is actually only about 15% what you put in. It's just it's worth so much, it's worth running the whole works for that purpose. What are you left with? You're left with about 60% yield of solid coke. Well, that's also a smokeless fuel because you've driven all the nasty tars and things out of it. So actually, every one of these old gasworks was producing 2 smokeless fuel products, but it was the gas that was the one that was really worthwhile to them. On the other end, if you're a steelworks, you don't care about the gas, and what you want to make is coke. So what you want is the same process, in the same pot more or less, to make metallurgical coke. That means it's technically suitable for a blast furnace. And the crude gas is now just the byproduct, and you don't even bother just selling it to people. You just use it crude as a fuel, sorry, to beg your pardon, in your own works. So there's the gasworks version. Here's what we call a coke oven in a steelworks, of which the last 2 are just dying. The one at Port Talbot has died, and the one at Scunthorpe has also died, hasn't it, Chris? Yeah. We now have none of these left working in the UK. Now, this retort is a giant version of the advanced version of the horizontal retort I was telling you about, where you push coke out at the end. So you have a big pusher machine, you can see it here. So the chambers here are tall and narrow. I'm afraid the lighting's a bit dark and you can't see them very well. There's lots and lots of parallel furnaces here. They're only about 1 foot wide each to get good heat transfer from the flames into the coal. And they're about 1 foot wide, 10 foot tall, and about 20 feet long. So you cook an enormous mass of coal in this thing, and then at the end of your 8 hours, you open the doors at the end. There's lots and lots of whole row of front doors all the way along it. Open the doors both ends, and this pusher pushes it out into wagons, and you then quench it under a water tower. Been a sight in every steelworks since about the dawn of time. That's now no longer visible in the UK. Let's talk about the R&D role a bit more. Okay, so we don't call it R&D much before 1960, but it is R&D, obviously. Yeah, Mr. Murdoch is conducting R&D in Redruth, is he not? The technology development's been continuous since 1973. So long as you kept using carbonisation right up until 1958, it's all about build a better pot. Can you make it bigger? Can you make it a bit more efficient? So there's progressive scale-up going on. That's very important. You've got to create an entire industry here. And there's this big change from batch production to continuous operation using gravity flow. And there's also this need for flexible gas output for the peak times, particularly the seasonal winter heating peak, for which you need these other processes we mentioned, producer gas and water gas. Just to remind you, throughout this period right up to 1958, we have no national gas grid. It's all localised production at village and town level. There's a few local city grids, Birmingham as an example. By the 1960s, those steam reformer plants, we've got a few regional medium pressure networks developing. There was one around East Anglia, for example. But it takes 1964, we start importing liquid gas into Canvey Island, coming up in a minute. And there was actually a spine line, as it was called, that ran from Canvey Island up to Leeds. This is before North Sea gas had even been discovered. The line was not to supply natural gas to people, the line was to supply natural gas to reforming plants so you could turn it into town gas. Okay, so what happens post-1958? Well, we've talked about these huge technology revolutions. We've got total gasification of coal. I showed you that plant at Coleshill. Only managed to make 2 of those plants, although they're giant plants. Then it's swept away by the steam reforming revolution using this cheap naphtha. And we've just completed that changeover, and North Sea gas comes on, and then we have to change over all over again. So the industry's been in total flux for 20 years, and that's pretty unique anywhere, I think. So I want to introduce you to my 2 heroes now. They're very well known in the world gas industry, almost completely unknown outside the gas industry, which is a shame. Frederick Dent on the left started his gas research career at University of Leeds in 1932, working on that thing I called the CRG catalyst, although it wasn't called that then. So this technology goes back a long way. He was extraordinary. He's widely regarded within the gas industry as the Brunel of gas after he started at Leeds. He was the founder director both at the Poole Research Station in 1940 and subsequently Midlands Research Station. He retired in 1967. I never got to meet him, but everybody talked about him. And he was dead by 1973. I think basically worked himself to death, a bit like Brunel. Over on the right, we have the businessman. We have Sir Dennis Rook. Now, he worked his way all the way up from apprentice on a tar plant to company chairman. In my opinion, that's how company chairman should be made. Somebody that fully understands how the business works and how the culture of the people in it work. Thank you. In passing, he had a key role in developing the world liquid natural gas tanker industry, which we'll come to in a second. No matter how senior he was, he remained an engineer-focused person. He was president of the Institute of Gas Engineers. He opposed the Thatcher privatisation in 1986 and got sacked for his pains. But he's a hero to all gas personnel. A few details about Dent. I mentioned 1932. He was widely regarded as a global expert on gas production technology, modern gas production technology from naphtha and coal and so on. He was the founder director. He really started work at Poole in 1940, and the primary purpose of that centre was to develop technology to make hydrogen for barrage balloons. Well, the hydrogen's got to come from somewhere. And he did the first work on direct hydrogenation of coal coming up. Founder director at Nechells, and then very shortly afterwards at Midlands Research Station in 1955. At the time when he first came to Solihull, he only had 50 staff. And his management technique was what he called hub and spokes. He directly man-managed 50 people. Their job was to run test rigs, quite often 7 days a week. And he did all the data analysis and wrote all the papers. Now, of course, that doesn't work when you have a larger organisation, but it did work with that size of team. He's an outstanding, charismatic, hard-driving man. He won the McRobert Award coming up for no less than inventing 5 different gas technologies in 1971. Retired, and because North Sea gas was coming in, he actually advised all his gasification research staff to emigrate to the States where gasification work was still going on, and he was dead by the end of 73. I want to put a few personal flavours into this talk. So one thing is everybody has an ambition when they join an organisation, don't they? And many people want to be chairman. I didn't want to be a manager flying a desk. I'm a tech head. What I wanted to do was to invent something that my hero Fred Dent hasn't thought of. We'll see how I get on. So Redruth has a rather long CV. I've listed it here. We can't go through it all. But highlight, he starts working as an apprentice on a tile works in London. It's part of the gasworks. Rapid rise to development engineer. That's quite a senior position in the South East Gas Board in only 1 year. Goes on to take a key role in introducing this oil reforming technology into the industry. 1959, he's deck engineer on the world's first liquid natural gas delivery. On he goes, helping plan the national grid, deputy chairman, founder chairman of British Gas Corporation. Opposes the politicians who don't want it because he doesn't want his industry messed around with and gets sacked for the privilege. Here's what the professional world think of him. Whatever the Thatcher government thought of him, that's what the professional world thought of him. He died much more recently in 2008. Another great hero. So let's do a little aside into liquefied natural gas. We now have 3 liquid gas import terminals in the UK. They're responsible for about 10% of the UK's gas supply. Where did all this technology come from? Transporting liquid gas at minus 160 centigrade in tankers. Well, everybody assumes it must be American. Well, it is sort of. It's a very strange story. The Chicago stockyards, you know, those people that slaughter tens of thousands of cattle from the American Midwest and turn it all into processed meat, which then goes on to refrigerated ships. They were saying, well, we understand all this refrigeration technology. What else can we do with it? Oh, I know, we could refrigerate natural gas and put it on the barge and move it around. So they actually originated the idea, and then the Gas Council jumped in with both feet in 1958 and said, we want a piece of this action. And then, of course, you've got a shipbuilder who's got to be responsible for converting the ship. So the world's first liquid natural gas tanker is called Methane Pioneer, and did its first delivery into Canvey Island in 1958. Things are very primitive. It's a converted old World War II Liberty ship, and the insulation on these high-tech tanks is balsa wood. That then becomes a fully commercial process in 1964, importing liquid gas from Algeria, who have much more of it available. And Canvey Island has more technical innovations because it's got unique, novel French design in-ground storage tanks. You only have to build a concrete lid, and the rest of the tank is frozen soil. The tank doesn't have any walls. Very clever. Unfortunately, not quite perfect, but we haven't got time for that story. That suddenly stopped in 1982 when the Algerians suddenly decided they were going to quadruple the price. Italy bought it instead because they were more desperate than we were. That's the thing about liquid gas tankers, you can actually move them around mid-voyage. What happens now is that Britain buys a tanker load of liquid gas, and by the time it's halfway to us, the Chinese have outbid us, and the things turn right for China. That happens a lot. So this technology is now a vital part of everybody's gas imports. So here's some pretty pictures. There's Methane Pioneer, top left. Here's the first commercial ship, 1 or 2, Methane Progress, 64, a long time ago, 60 years. Here's a cross-section of a modern one with spherical tanks, what's called the Moss system. And here's the lid of one of these revolutionary underground gas storage tanks at Canvey. LNG is now responsible for about 10% of all the gas that moves worldwide. It's a very clean fossil fuel versus oil and coal. Yes, it's still a fossil fuel. I'm not pretending it isn't. But it's a lot cleaner. It's got half the carbon dioxide emissions of coal. Large numbers of countries exporting it. Large numbers of countries importing it. Amazingly, we've had this shale gas revolution in the States, which is still gathering pace, by the way. The USA, from being a major gas importer, is now a liquid gas exporter. And they're also exporting ethane that's extracted from the gas as a petrochemical into Grangemouth. Japan runs on nearly 100% LNG imports, and the Chinese are gradually gobbling up the world's LNG market. Right, let's go back to the mainstream. Let's go back to North Sea gas. There's an unknown story on North Sea gas. It didn't quite develop the way people think. The public sort of think one day there was no North Sea gas, and the next day it was 100% of our supply, or at least within 10 years when you built the grid. Didn't quite work that way. Discovering gas fields is a very gradual process, and oil fields. We're still discovering new gas fields today. Nobody to this day knows how much gas is actually in the North Sea. However much geology has left us that we haven't discovered yet. But each field very rapidly declines in gas flow rate after you've opened it. Not surprising. You're sucking on a straw that's about 9 inches diameter from 2 miles deep in solid rock. As soon as you suck, the pressure goes down, so the flow goes down. So very rapidly, the balloon deflates. And so rough field off the Humber declined so fast that after only 10 years of operation, it was bought by British Gas to turn it into a gas storage field. And we pump gas back into it when it's surplus in the summer and then bring it out in the winter. And that's how we do that summer to winter swing. I mentioned about half of the North Sea gas being on the Norwegian side. So one thing is the gas is only being discovered gradually. The second thing is that the demand for it is rocketing. So the industry's got to run very, very hard to stand still. So when I joined Midlands Research Station in 1973, believe it or not, the official strategic target was we might have to start making some man-made natural gas substitute, SNG, as soon as 1984. Discoveries were so rapid from 1973 to 1984 that by 1985, we expected we got a surplus that would last us until 2032. By the way, North Sea gas doesn't suddenly stop. The wells don't run out. The flow rate just gets lower and lower gradually over decades, and eventually it becomes so low it isn't worth getting it out economically anymore. So gas fields don't suddenly die. That's not how it happens at all. Then there was this big strategic decision by Mrs. Thatcher and most of the rest of Europe, I hasten to add, to go for gas-fired power stations. Well, each gas-fired power station, on average in Britain, uses about as much gas as a city of 200,000 people. So your surplus position until 2032 rapidly collapses until we eventually crossed over in 2003. And the UK is now importing over half its gas. We could argue all night about whether that's right or wrong. So there's a gas decline curve for one well. I've given the total in years across the bottom here. The flow of this particular well was down to 1/10 within 8 years. So that gives you some idea of what we're dealing with. Okay, this is my come clean slide. There was huge amounts of technology used in exploiting North Sea gas. It wasn't us. I'm not going to pretend Midlands Research Station invented this. We had no experience in natural gas exploitation at all, and certainly not offshore. The Americans have been exploiting their natural gas since 1940, thereabouts. So they had decades of experience. So all the technology that went in the North Sea originally was all American oil company stuff of variable quality. But we did rapidly establish gas rig production yards in Scotland to save having to tow gas rigs across the North Sea, across the Atlantic rather. And there was a rapid growth of a UK-based service sector, all the divers and support crews and food and everything else you need. So I've listed there the main bases that the North Sea fields are supplied from. What British Gas did do was encourage the growth of the entire thing. As a monopoly purchaser at the beach, as a nationalised company, they were able to say, basically, you supply it and we'll buy it. Well, that's a bankable guarantee for the companies to go and get the investment they need to put the gas rigs. The gas rigs on average cost about £500 million each, by the way. There was an attempt to influence safety standards, not terribly successful. We helped with the rapid learning curve of all the UK suppliers so as UK could learn how to do this. And then the Engineering Research Station was founded in 1968 with the specific aim of developing all the pipeline engineering that was needed for the onshore grid, the national gas grid I've already shown you. The National Transmission System, as we call it, NTS. It's the world's safest and most reliable gas grid by a long chalk. There have been 0 failures on the national system ever since it started. So let's look at the research stations. I've listed them here. And you can see some of them are quite old. They go way back in even before nationalisation. So these are old local company research stations, gas board research stations. But here's the list. So MRS is the third, and engineering research station, I just said, is the new baby on the field. But we've also got some quite large field test centres where bigger stuff is tested, and I've listed them there. Spade Adam is fairly near to Carlisle, fairly near to Hodrien's Wall. So by the time we get to, let's say the 70s, we've got about 1,000 staff in R&D. It's the world's largest integrated gas research programme. And there's a budget of 55 million a year, which has been sort of forward guaranteed by the national company for at least the next decade. So I've listed here the missions of the individual research stations. Watson House was the centre of, that was in Fulham, by the way, was the centre of expertise for domestic appliances, gas cookers, gas fires, that kind of thing. London Research Station, also in Fulham, was the fundamental department, all the basic level stuff, first exploratory steps. We used to call it the University of British Gas. Midlands Research Station was where gas production and industrial burners were scaled up, and also the main centre for looking at gas safety issues. And Engineering Research Station was pipeline engineering. Then you've got these field test centres. Spade Adam is the big boys' toys for people that like blowing things up. It's a very remote site. It used to be an RAF rocket testing station. And you can have full-scale gas explosions there with sort of fireballs, 30 metres in diameter, this kind of thing. Bishop Auckland was used to test pipeline integrity and accuracy of large meters. Fold near Boulton did medium-scale explosions and fires. And Coleshill was quite close to us, and it was just used for general purposes connected with the research. So the general themes of all this, what makes research in British Gas rather special is that this is not like a university at all. This is very much the development end of research. It's heavy industrial R&D, and the reason for that is that virtually everything's under high pressure, because you're looking at stuff that's going to be interacting with the national grid at 1,000 psi. So we're not dealing with test tubes here, it's big boys' toys. So these test rigs are costing sort of between about £500,000 and £12 million each in pounds of the day. Multiply that by 4 in your head. They are doing the designs for full-scale plants. So I beg your pardon. That's going to cost £500 million to £1 billion each, because that's how we do it these days. Big stuff. Economies of scale. So the test runs are not being done randomly. They're being very closely guided by computer simulation, which I was responsible for optimising the cost and efficiency of full-scale plant. And then that guides the test runs you do. It's nearly all high-pressure engineering, as I said, and there's a lot of large-scale pilot plant testing going on. For example, full-size industrial burners being tested. It was dedicated to technical excellence back in the nationalised days, with adequate budgets to make that happen. And we had very, very close relationships with the engineering departments of the company and the business departments, and very close relationships with the equipment manufacturers. It's very much applied research. This resulted in a global level R&D leadership, and particularly global level leadership in safety research. Let's just take a quick look at the industrial burner development that took place at Soho. I'm just going to highlight a few key inventions. Stuff that came out of Soho totally revolutionised the metal bashing industry. We're dealing with high temperature furnaces like this running at maybe 1500 centigrade. So the first invention is the recuperative burner. Recuperative means recovering your heat. So we've got a normal burner on the right hand end, and what we've got just behind it is a heat exchanger. So as all the hot gases going out on their way to the chimney are exchanging heat with the combustion air coming in. You can't safely heat the gas, you can heat the air. For every kilowatt of energy you put into the air, that's a kilowatt less fuel you've got to burn. So these things are like doubling the efficiency of a gas burner. There's a limit to the temperature this type can achieve. So then we go to the regenerative burner. Now this is a bit more complicated. Quite a lot of you will know this fellow on the left. These are things called cowper stoves that are used with every blast furnace. It's a cyclic process. You've got enormous towers full of a Jenga pile full of brick, like about 200 tons in each one. You switch the valves, you heat one up with the hot exhaust gases coming out of the blast furnace at about 1000 centigrade. When it's reached that temperature, you switch it round and you put the combustion air going into the blast furnace through it to recover all that heat. So you can now recover heat to much, much higher temperatures. Well, We can't really have stuff that size hanging on an industrial furnace. So what you do is you use pressure and velocity. Most industrial burners are fired at much higher gas pressure than domestic gas burners are. Think Bunsen burner. It's that sort of intensity. You can also increase the velocities by deliberately blowing the air in very fast. And that magnifies the rate of heat exchange between the gas and the brick, or whatever, alumina balls in this case, in these regenerators. And instead of taking 10 hours to heat one up, you can heat up in 10 minutes. So these things are now going 60-fold as fast, which means they're a 60th of the size. So your recuperator is now the size of a dustbin. So you can hang these all around the furnace. Now these are used all over the world now. They've won all sorts of awards. Then we went even further. A lot of metal bashing operation. Well, first thing to know is that big furnace I showed you a couple of slides ago, its thermal mass is so big, all the ones that used to be used with coal and oil heating, they're so big they simply couldn't be switched off. They not only couldn't be switched off for the tea break, they couldn't be switched off for the weekend. So they ran continuously whether anything was in them or not. Very, very wasteful, very expensive. What can we do about that? Well, coal and oil are dirty fuels, which means you can't contact them direct with the metal. That's why the burners are on the outside of a furnace. What you can do with gas is it's a clean fuel, so the metal will tolerate having a gas flame directly against it. So now you can have something like a Bunsen burner on steroids. You can heat a piece of metal in literally about less than a minute. This is a steel rack conveyor belt that's racking these things through this burner enclosure. And there's so little thermal inertia in this, you can now switch the thing off for the tea break. So just the fact you can switch it off has more than halved your energy consumption. This kind of technology reduced energy consumption in the metal bashing industry in Britain by about tenfold. Won all sorts of awards. Very occasionally, you've got very sensitive processes that can't tolerate having the gas flame in direct contact. So we developed this fella. It's basically a gas-fired immersion tube. The gas flame is totally enclosed. You can see we're using an internal recirculation tube again. So this creates a nice even heating all over the outside of the tube, and the gas isn't contacting. You can use these as an immersion tube directly for boiling liquids, say in a process plant. You can use them for very sensitive metallurgical operations. A lot of you will be familiar with this technology. You used at much lower temperatures. Look up in the roof of the average B&Q and you'll find these radiant heaters, which are using the same technology at a lower temperature. So what's all this industrial burner R&D doing for us? Well, many members of the public say to me, why on earth would British Gas spend millions and millions of pounds developing burners to burn less gas? It's a very interesting question. Well, the company's that strategic. It's figured out that what's important is not how much gas you sell to each customer, it's how big can you grow your market share. You make it more efficient and cheaper for them, and lots more people will stop using coal or oil and use gas instead. And that results in things like this. So this on the right, it's a snapshot from 1984, and it's all the heat supplied in the UK for everything except road transport. Transport's a special case because it's nearly all running on petrol. You know, it requires a portable fuel. But if you take everything else, all the homes, all the industry, gas was supplying 44% of all the heat used in the UK. Most of the public are completely unaware of this number. If you ask them to guess, they'd probably guess 20%, 15%. It's the biggest single source of energy in the UK, which makes what we're going to do next with the gas industry to make it green really very important. Let's have a quick look at the safety R&D. This place called Spade Adam. It provides global leadership, not just for the gas industry, for the oil industry as well, because an oil explosion and a gas explosion are not that different. It's still expanding today. It's the one bit of R&D that's really survived in the world. It's coordinated a UK explosions R&D group for over 35 years now. It has global leadership in both the doing and the prediction of large-scale fires and explosions, developing all the predictive codes that predict what a big gas explosion will do if it goes off. The expertise is greater than the Health and Safety Executive has. That's widely recognised. Some of you are old enough to remember the dreadful Flixborough chemical plant explosion back in 1974, a plant making nylon, where there was a mid-air explosion of a gas cloud. It flattened most of the plant and killed about 35 people. That was something that at the time people didn't even know could happen, a gas explosion in the open air. It's a thing called a BLEVE, a boiling liquid evaporating vapour explosion, and it's extremely violent. You'll remember the Piper Alpha disaster when an entire rig burnt out completely and collapsed into the North Sea, and most of its crew died. There was about 100 deaths. 1988. Investigating why that had been so devastating, why it had destroyed the entire rig, led to a complete step change in models of how fires and explosions are managed. Just in passing, they do other things. The TV asked if they could actually blow up a model, a full-scale model of the House of Parliament at the time of the 1605 gunpowder plot. Just Google it. Go and play the plot reconstruction. You'll find it. I don't have time to show it you now, unfortunately. Here's a few examples, just a few pictures in the mind. This is the main pipe trench. This is a length of full-size 1,000 psi pipe sitting in a shallow trench. Now, why is it sitting in a shallow trench? Well, the original pipe's buried under soil, but as soon as an explosion occurs, all that soil gets blown away, and the thing is now sitting in an open trench. This is a computer graphic, but it's a very nasty example of something that's nicknamed the banana split effect. If there's a crack in the pipe wall, the massive stresses can cause the whole pipe to unzip. And that process can go on for more than 10 miles. It's an absolutely devastating event. And that's why all gas pipelines have to be checked for integrity to make sure the cracks are small enough that doesn't happen. And we know exactly how big a crack is tolerable. This is the latest kit. This is brand new. This is only from about 5 years ago. World's largest explosion chamber going off. Oil and gas companies all over the world hire space at Spadeadam to do things. Why are we spending £10 million a year on gas safety research? Because this is what happens if you don't. This is not a picture of the wildfires from last December. This is a man-made disaster right in the middle of San Francisco in 2010. Just the same effect as a wildfire. Killed quite a lot of people. That's why you need this kind of expertise. Just want to talk very briefly about safety and perception, because the public perception of safety of these industries is completely wrong. Everybody knows about gas explosions in houses. They're always on the TV news, aren't they? Because it makes good TV. Oh, how many are there? Oh, 270 a year. Shock, horror, good heavens. Well, what's causing them? Well, very few of them are the British gas mains under the street. The vast majority are in houses or blocks of flats. And an awful lot of them are self-inflicted because some idiot's trying to bypass the gas meter to save money. Many more are because they're failing to pay for their annual gas safety checks that they're all supposed to have. But it makes good TV and it usually gets reported. Well, what's the death toll? Over a 5-year period, quite recently, the death toll was only 5 deaths, so 1 a year, and just under 200 injured. Well, there's another big problem, carbon monoxide poisoning. If your burner is badly adjusted, it can produce carbon monoxide instead of carbon dioxide, and it's a very poisonous gas. You all get warning signs about it from your gas company, I'm quite sure. What does that cause? Well, about another 200 deaths in 5 years. Well, what's happening with electricity during this time? 70 deaths and 1/3 injuries a year. Do you ever hear any of that reported on the media? No. So gas is actually relatively statistically very safe, especially as the industry transports 3 times as much energy as the electricity grid does. Let's look at a few awards. Quick show of hands. Anybody heard of the MacRobert Award? No, I thought not. Well, you jolly well should have. It's the nearest thing there is to a British Nobel Prize for Engineering. It's named after a famous industrial entrepreneur who died back in the 60s. It's been going since 1969. It was funded by his widow. And nowadays it's administered by the Royal Academy of Engineering. They're the ones who do the judging. It's awarded to companies, and it's only awarded for technology that's actually being used for real. So, for example, the first winners were the design for the Severn Bridge deck and the jet engine that powered the Harrier jump jet aircraft. Most UK winners have only won it once, and most have only won it for a single technology. British Gas have won it 3 times. 1971, it was awarded to Denton's team for not 1, but 5 different inventions of modern gas production processes. These are naphtha reforming things we've been looking at. 1989, so Engineering Research Station for the Intelligent Pig gas line inspection vehicle. Well, a pig is something you push through the gas pipe under the gas flow to clean it out. The Intelligent Pig is like a spacecraft in a gas pipe. We'll see a picture in a minute. 1995, there's the ultrasonic domestic gas meter with no moving parts that has totally revolutionised the reliability and accuracy of domestic meters. You'll all have one in your house. So there's 4 of the 5 processes that won in 1971. There's Denser, 4 from left. I know 3 of the other men. There's the Intelligent Pig top left. You'll have seen these if you've ever watched Bond films. A beast similar to this appears in 3 different James Bond films where people are being transported through pipes for spying reasons. Or one of them's got a nuclear weapon being transported on one. You see all these funny little arms sticking out of it, these little things. These are feeler gauges that are feeling the pipe wall. And they're using sophisticated techniques like magnetic fields and ultrasonics to detect tiny little cracks that are too small for you to see. These things are extraordinary. You have launcher stations where you can launch them. It's just basically a T-piece off the edge of the pipe. You can depressurise it, open the door at the end, shove one of these in, and then swing the gas supply around and it'll pop off into the pipe. They run for maybe 50 miles. They're completely independent. They're in the gas supply. They have their own batteries, their own data recording. It's basically a spacecraft. It's completely remote from human assistance. They run for 50 miles, they pop it out, and they download 50 miles worth of data that's accurate to the nearest half a centimetre. Every single crack in the pipeline is one. We do these routinely. Every British gas pipe gets one of these runs several times a year. If you don't, you get things like that San Francisco event. Here's the ultrasonic gas meter. They're rather boring, I'm afraid. It's the stuff on the outside always is, but it's got no moving parts on the inside, so it doesn't look much better there. And then there's all these advanced burners I mentioned, including an extra one I didn't show you called the direct contact water heater. So here's my home. A few little details about it. Main missions again: gas production, natural gas purification, industrial scale burners, and gas safety. 6 major buildings, 2 of them gasification, my bit. 4 major divisions, 3 doing R&D and 1 being engineering support. But also we had on site the School of Industrial Field Management that was training most of the fuel management professionals for every company in the country. SOFM for short. We always used to call it the School of Free Meals because the trainees were always given lunch for free. And we managed 3 outstations at Coleshill, where I did some of my work, Fald and Spade Adam. You need an attitude of mind if you're going to work on high pressure equipment at high temperatures. 1,000 psi or 4,000 psi if we're dealing with the storage facility at Hornsey, no problem. Engineers from MRS more or less wrote the British standard for pressure safety. 1,000 degrees centigrade, glowing white hot, well, yellow hot anyway, no problem. Flammable gases, well, that just goes with the territory. Everything's flammable. But hydrogen, which is explosive, coal dust, we're gasifying coal dust in some of these rigs. Toxic carbon monoxide, need I go on? A lot of the rigs were still insulated with asbestos when I first arrived. The key issue is respect it, don't fear it. If you fear it, get out of the kitchen. What keeps you safe is your expertise. Ditch the safety manual, doesn't matter how many pages it's got, a safety manual will not save you if you don't know what you're doing. And highly experienced technicians that aren't going to make a mistake when they're putting all these high pressure rigs together. So we plan for risk. There's these things called HAZOP, Hazard and Operability Study. When each new rig's being designed, you systematically have a team, typically about 6 to 10, that systematically go through every single event that could cause this plant to fail. And you go through what you're going to do about it. So you try and avoid risk where possible, but where there is risk, you deal with it. Because we were the major fire risk in the whole of Solihull, we had our own fire brigade. Just so as we could start dealing with an event before the public fire brigade turned up. And all staff were trained on firefighting. And it's an amazing sight watching a secretary with a fire extinguisher on tackling a 3-foot square tank of blazing petrol. Very extensive fire alarm system, as you'd expect, a formal evacuation plan, permanent site safety committee. I was a divisional rep on that 1 year, with British Gas headquarters keeping an eye over our shoulder. Our own permits to work system, monitoring contractors coming onto site. Sorry. I was permit to work signatory for a couple of years in my department. There's our on-site fire brigade. Their equipment was old. They had their own firefighting appliance. Just an example of the sort of things that went on. I was talking about attitude of mind. The CRG process, naphtha gasification, well, that was basically petrol. So we got 3 20,000-gallon tanks of it on site, and they've got to be refilled through normal road tankers. So it's a regular routine. A road tanker turns up and somebody's got to unload it. Well, they're pumped into the tank, which is about 20 feet high, with a compressed air pump. And it's outdoors, and that's a problem, as we'll discover. On my very first turn to do this, in a month of rising, it was very nearly the end of my career. Some idiot goes and arranges a delivery on November the 5th. Not a good idea. I protest very loudly. Don't worry, he's coming in the morning, he'll be gone by 4 p.m, no problem. Well, of course, there's traffic delays. He doesn't arrive until 4 p.m, does he? It's freezing out there. It's dark. The pump keeps icing up. My job is to stand out there in the freezing dark, playing a steam hose on this line, on this pump, to try and unfreeze it. I plead with him to take his half-empty tanker away. Oh, I can't do that. It'll upset my schedule tomorrow. So by 6 p.m, tanker driver's indoors having a nice cup of tea in the warm. I'm out there in the cold, and the rockets start coming across the canal from the houses opposite. That's how I wrapped up. This is how it all ended. After privatisation, the last act of defiance of the old nationalised British Gas was to build us a brand new national research centre at Loughborough. It's on the end of the university site, for 1,000 staff with expansion to 1,200. The old MRS site was sold off for housing. Well, was this world-class gas research centre properly recorded by either the English Heritage for the buildings or the Science Museum for the equipment? No. Subsequently, when we moved to Loughborough, large test rigs continued to be scrapped. The world's largest gas on carbon storage, that was my project, a ton of carbon. World's largest project for making natural gas hydrate, which is gas trapped in ice cubes for transport from one country to another, scrapped. That was my project. Well, in fact, all 3 of these are mine. A totally unique deep rock cavern leakage simulator. We were simulating a piece of rock 1,000 feet underground with a crack in it and actually measuring how fast gas got through it. British Gas did self-fund, thank God, a proper history book for each site, one for each of the 4 research stations. So, but no official interest, no official funding. By the way, this is the steel sign off the front door, which the director very kindly gave me when we were walking out the door. So, very much end of an era. So what happened afterwards? Well, the first bit's there, 130 million, this new research centre we moved into, with intended expansion room. Now, originally it was 80% business unit funded. That means the business unit had to agree that the work was necessary. And 20% of it was corporate funded, which meant you could do some longer term stuff. Well, the corporate element had completely evaporated within a few years. So now a piece of research would only be funded if the business unit actually wanted it now. A new director was appointed. We'd never ever had a business director who wasn't a proper researcher. This chap was from a business department. He got no R&D background at all. I think he must have done enormous damage to the external perception when he went to meetings with other R&D directors elsewhere around the world. He was obsessed with cost saving. He regarded staff as a cost. Staff are never a cost in a research centre. They're the resource. Anyone who understands how R&D works in a large company knows jolly well that if anybody's doing the research right, the savings the company makes in its entire operation should be worth at least 10 times the cost of the R&D. But those savings don't come back to the R&D department. The company just knows that when the R&D's done, massive savings will be made. There was the deeply mistaken policy here at Loughborough to try and make R&D an immediate profit centre. In other words, research results had to be sold for cash. That very, very rarely ever works because there's no accounting in it for the benefits of the vast cost saving the company's making from the results. We were hived off as a separate company called Advantica PLC. Well, what does that mean? Doesn't have gas in the title, doesn't have technology in the title. It's vague, sounds good. One of our biggest problems is the global expansion of British Gas. British Gas was now allowed to operate in any country in the world. The business units could go on to expand globally and increase their business tenfold with no new technology at all. And they were really only interested in short-term wins, most of which was cost saving and safety work and technology support consultancy. So they wanted us all to keep technology watch on what was going on in the rest of the world. I did a lot of that. So it's observe, don't do. And then, of course, the political fragmentation of the business into lots of different bits makes R&D funding much more difficult because you haven't got a central research anymore. So the first redundancies occurred within 2 years. There was active encouragement for people like me to go. That's a polite word for it. By 2003, we were down to a quarter of the staff, and the building had been sold off to Loughborough with us hiring a quarter of it back again. The BGL gasification process, the advanced version of that gasifier you saw at Coleshill, well, British Gas sold off its rights to that to China, or the privatised company did in 2005, just as the technology started to sell in China, amazingly. Very strange decision. The big test centre in Scotland had closed down, and there were only 2 staff left dealing with that bit of technology. The whole R&D business was sold off to Germanische Lloyd in 2007. That's the German end of Lloyd's of London. And that in turn was merged with DNV of Norway. Well, both of these companies are certification companies. They certify a brand new ship as being safe for use, that kind of thing. So the bits of the business they really wanted were something they could make money out of by doing certification services. They didn't really want the R&D bits at all. It's a great shame. So increased focus on short-term cost saving. So, conclusions. The UK gas industry has been research-based ever since 1793. We just don't tend to apply that term to it. Gas technology and the UK's global leading role in it deserve to be at least as well known by the public as oil technology. It's the world's safest gas system. We've talked about 2.5 complete technology revolutions within 20 years in the 60s and 70s, saving a dying industry. The problem in all of this, of course, was that from 1970 onwards, changes in the political environment and changes in the relative cost of different things you can make gas from are moving faster than the technology could possibly keep up. You're running very hard to stand still. This synthetic natural gas we were able to make, a man-made natural gas equivalent, could have been greened up for the 21st century using bio-waste. The government has no interest. I wasted 14 years of my time as a private individual trying to kick the door down at the Department of Energy with no success at all. So, what's the big picture? Well, privatisation has done wonders for gas shareholders, of whom I am one, and one or two of you maybe, and customers have had a very good deal. But it's been a disaster for energy research within the UK, and it's been a disaster for long-term strategic planning of the industry. And as a result, the UK gas industry is now under direct political threat as I speak, because the government recently decided they're going to close it down by about 2040, and you're all going to be forced to buy an electric heat pump at a price of over £5,000 each. And that's because they hadn't got a credible alternative working together as a cohesive industry. And I've always said for my whole career, energy strategy is far too important to be left to politicians. So if we run out of question time, there's my contact details if anybody wants to make a note. Happy to take any questions.
Thank you, Chris. Very lively presentation. Unfortunately, so good. It's leaving us a bit short on time.
I know.
Not to worry.
There was a lot to cover. You can have part 2 another time.
Yeah. Any questions, folks?
If you do have a question, obviously try and keep it brief. Wait for me to bring the microphone over so that people can hear
One
you.
on the left here.
Yeah.
If you're at home, then you can use the chat function on Zoom.
Or pick up my contact details. Yes, sir.
Thanks. Just 3 sort of comments, basically. There was a film on Talking Pictures TV. I didn't really watch it. they have a look at life series they put on.
Yeah.
And one of them was about that those Algerian
Oh, the
tankers.
liquid natural gas tankers, yes.
Yeah, it was worth seeing. The other thing was, I can remember, I was at Solihull, where you used to have those gas production units, and in one of the winters, they continually broke down because of the cold weather.
Uh-huh.
And they said on the news, they're starting to cut the gas off to the
Yeah.
industrial customers. What was causing that?
The reason for that is that the old-fashioned gasworks, the coal gasworks, there was a fair bit of water vapour in the gas. So in cold winter temperatures, the gas could literally the water content of the gas could literally freeze in the underground pipes and block them up.
And the other question was, when you mentioned about the first building of the house that was lit by gas, where did you say it was?
Where? Redruth.
Oh, it's Redruth.
1793, and it's still there. I showed a picture of it.
Yeah,
You
thank
can
you.
visit the museum there.
Lovely. It's the one that's open Friday mornings.
Hmm?
That's
Yeah.
the one, yeah.
Friday mornings only, unfortunately.
Thanks. Thank
Very
you
good
very much.
exhibition on Murdoch and his work in there.
Thanks.
Just in passing, Murdoch was developing the world's first steam-powered vehicle at the same time.
Chris, there's a question just...
Oh, right, fine, yeah. R&D into developing steam reform, it shut down when it became obvious. Oh, right, yes, that's an extremely good question. Yeah, what I have not had time, because this talk's been so rushed, I mean, I could go on for 4 talks, is that just at the time that we were ceasing to use reforming in the UK, there became a huge opportunity to export the technology to make man-made natural gas, this stuff I call SNG, synthetic natural gas, in the United States. It's an extraordinary story. I could do an entire talk about it. Between 1972 and 1978, so only 6 years, they built enough gas-making capacity in the United States, where they had had no gas-making capacity at all since about 1960, to make an amount of gas equivalent to the entire gas use of the UK. Now, that was only about 5% of the American gas use, but the fact that they were able to build a plant that quick was amazing. British technology won 90% of that business against fierce German and Japanese competition, and I bet none of you except Chris Allen have ever heard of it. It's amazing how useless our press are reporting big, multi-billion-pound gas successes. So that's the answer to that one. Oh, it's Fred. Fred ought to know better.
Hi, Chris.
Yes,
I'm looking forward to part 2.
thank you.
Can you, just for those who don't know,
Yeah.
explain which one of those processes produced high-speed gas?
Oh, yes. High-speed gas was just a marketing name. You'll probably all remember the posters, those of you who are old enough. High-speed gas was the marketing name that was initially used for that reformer gas before North Sea gas came along. There was a kind of technical thing in it because the gas included a lot of hydrogen, which has a very high flame speed, but they just thought it was a nice, trendy, modern-sounding name. It wasn't really meaningful. They continued using the high-speed gas term for natural gas as well.
Right, I think given the time, we'd probably better call it to a halt there.
I think so.
There's a few little goodies on the table if anybody wants to come have a look.
What do we say? Thank you very much. Really wide-ranging.
Big tail.
Yeah.
Big stuff.
Quite amazing. I'm glad to discover what you used to do. So thank you very much. May we show our appreciation again?
Thanks very much. It was a privilege working there. It was truly world-class work.
Right,